Alright, in this video we're going to look at this system that's drawn here, and we're going to try and figure out what range of masses could hang at point A, here's A, and allow this system to stay stationary. The coefficient of friction between this 5 kilogram object and the surface that it's resting on is known at 0.2, and so if this object is really, really light, what will happen is the entire system will tend towards the left, as the force of gravity on that 5 kilogram object will be enough to accelerate it down. And if the object at A is really, really heavy, then the whole system will tend to the right, and as a result that object A will pull everybody down. But what I think you can see from this is that there should be a range of masses where the 5 kilogram object isn't heavy enough to overcome A and that force of gravity or force of friction, to where A isn't heavy enough to pull the whole system to the right, that will allow this system to remain stationary. What I'm going to do then is I'm just going to come up with what the different forces are on the different objects. This 5 kilogram object has a force of gravity that's equal to mass times g, which is equal to 5 kilograms times 9.8 newtons per kilogram. And I'm not really going to pay attention to signs right now because I'm going to have to interpret directions in this problem. This 5 kilogram object has the same mass, so it's going to have the same force of gravity. Since it's resting on a tabletop, a normal force will balance out that force of gravity. And since I have a normal force and a coefficient of friction, I can find a magnitude for my force of friction. And that works out to 9.8 newtons. Finally, I have the force of gravity acting on object A. I don't know the mass of object A, so all I can say right now is that that one's going to be equal to 9.8 m. Let's keep in mind with this frictional force that this isn't really equal to this. This represents the largest value that it can take on before the system starts to move. So the frictional force is actually less than or equal to that 9.8 newtons. Now I'm going to consider the system as a whole. Its mass would be 10 plus whatever A turns out to be, or the mass of A. And for the sake of argument, I'm going to put the force of gravity, this 49 newtons, acting this way. I'll put the force of gravity on object A going this way. And so we can see that those two forces oppose each other. And then the only force that I haven't included is my force of friction. To understand this, the trick with this question is going to be that force of friction could be acting in either way. It depends on whether we're interested in the minimum or the maximum mass of A. Let's start with the minimum. If A is very small, then this 5 kilogram object is going to appear relatively large, and the entire system will attempt to move to the left. To oppose that then, the force of friction, 9.8, will act to the right to try and stop it. We use the maximum value for the force of friction because we want to make sure that we're getting our end point, or we're getting the minimum mass that we can get. If we want it to be stationary, we know that the net forces must add to 0. And so what I'm saying, I'll call this direction negative, is that negative 49 newtons plus 9.8 newtons plus the force of gravity on the hanging object at A, which I don't know. So this is the force of gravity on the 5 kilogram hanger, and this is the force of friction, plus the force of gravity, all have to add to 0. So 0 equals negative 49 plus 9.8 plus 9.8 m. Bringing these two guys to the other side and adding them together, I get 39.2 newtons is equal to 9.8 m. And then if I divide both sides by 9.8, I'll see that my mass is equal to 4 kilograms. So all the way down to 4 kilograms, the force of friction acting on that 5 kilogram object will be enough so that that 5 kilogram object can't overcome A and the force of friction. So anything greater than 4 kilograms isn't going to move. The 9.8 will, if it was 4 kilograms, it would go to 9.8. But let's say it was like 4.5 kilograms or something like that. It wouldn't be 9.8. It'd only be as big as it needs to be to keep the system from moving. That gets you your minimum. What about your maximum? Doesn't like to move over sometimes. There we go. Again, we'll consider the system as a whole to do this, 10 plus A. We still have a 49 Newton force acting in this direction. I'll still call that the negative direction, and that would be associated with the force of gravity acting on this 5 kilogram object. Now, though, we're going to assume that A is very, very large. If A is large, it's going to pull the system to the right. So instead of the force of friction acting to the right, where it would encourage the movement of the system, the force of friction, if this system is trying to move this way, will work against it, and so the force of friction will point this way in this case. So the force of friction here would be 9.8 newtons, but as opposed to being in my positive direction and trying to keep the 5 kilogram object from falling, now it's in my negative direction and trying to keep the object A from falling. And I still have the force of gravity acting on object A. Again, for these to be stationary, we have to say that the net force is equal to 0. And that's going to be equal to my Fg on my 5 kilogram hanging, so I'll call that Fg5, plus my force of friction, plus my force of gravity on object A. Now I know this is negative 49 newtons. The force of friction this time is negative 9.8 newtons. And this is 9.8 times my unknown mass. So adding those two and bringing them to the other side, I get 58.8 newtons is equal to 9.8 m. And if I divide both sides by 9.8, my maximum mass is going to work out to be 6 kilograms. So any mass between 4 kilograms to 6 kilograms will allow the system to be stationary. Less than 4 in the 5 kilogram on the left hand side would win, everybody go to the left. More than 6 and the A would be too big and everybody would fall to the right. The trick here is that in the two different situations, the force of friction acted in different directions, and that allowed the mass, based on which way the system would want to go, and that allowed the mass to be different, or the mass to have a range. The fact that all the numbers in between are okay comes from the fact that the force of friction is only as big as it needs to be to balance the motion. It doesn't have to take on that 9.8 Newton value. That's just the biggest value it can take on. So, consider the forces acting on the system, treat the system as a whole, set the net force to 0, put the force of friction in one direction to get one mass, put the force of friction in the other direction to get the other mass, and as a result you end up with the 4 to 6 kilogram range.